So, hello everyone. Thank you for coming to the talk. I'm going to tell you about reparametrization invariance in geometric deep learning and the ways that this can be achieved as well as possible, and the ways that my student Thomas Besnier has been applying it to human body shapes and face deformations. So it's my first time presenting all of it, so sorry if it's a bit rough. Hopefully I manage. And sorry for the delay, it's because I had to go get back my credit card, which I had lost somewhere, so sorry. Okay.
But did you find it?
Yes, yeah, that's what I was trying to tell you, but...
You have 57 slides?
Yeah, well, if it's too long, I'll just... because the problem is, I didn't know really which part to focus on to make sure everyone understood. But anyway,
the first one is about Sub-Riemann.
No. There's no mention of Sub-Riemannian geometry in infinite dimensions, sadly. Okay. So basically, it's gonna go like this. So first, quick introduction on neural networks. I don't know. I'm not a specialist of neural networks, but I don't know who knows about them and exactly how it's done. In my team in Lille, no one really does them. So it's usually useful to just have a quick recap. And then we'll talk about the kind of things we have done during Thomas' thesis. I present a quick summary of everything we tried to do during his 3 years PhD. And then I'll give you some examples of ways to achieve reparametrization robust neural networks for surface deformations. Okay, so basically machine learning and usually neural networks are, from what I know, applied to machine learning. Basically, you want to approximate a map that is usually impossible or very hard to truly compute or formulate mathematically. So, for example, there's a lot of examples on images, but basically, you give your program an image and it tells you, is there a cat in the image? You can also try something that makes a person smile when they had the neutral expression initially, things like that. So it would be very hard to just find a mathematical formula that does this. And so instead, what's done is, you try to approximate it using a subset of functions that have some parameters. And then you take a lot of a lot of data for which you know what the answer would be, right? So a lot of data where you know, okay, lots of pictures where this picture has a cat. Okay, I already know it has a cat, or it doesn't, and I already know it doesn't. And then you just try to find a function within the subset of functions that you allow that comes as close as possible to having the correct values on your training set. Right? Of course, there's other ways to do it, you have probabilistic ways, but that's the most basic way. And neural networks are a specific way to do this that uses composition of many simple maps, right? So you start with your data X, and then you apply to it a first function, and then you get Z1, and then you apply to it a second function, and you do that a lot, and you end up with some sort of final output. Usually the Z's can be called hidden layers or features, things like that. But anyway, the main idea is for neural networks usually, the key to have them work very fast, or at least to optimize them very fast, is that there are two kinds of general layers, at least those that I'm going to consider. First, ones that are affine with respect to the variables, but also linear with respect to the parameter. Okay, so these are called linear layers. And then you add activation layers, which basically are just you get a function with one variable, right, from R to R, which is nonlinear, and then you just apply it coordinate by coordinate on your variables, okay? And so one that's commonly used is the rectified linear unit function, but that's also called just the positive part, which I prefer to just denote it by a plus as an exponent. Okay, and usually, you just follow, you do a linear layer and then activation layer and then linear layer and then activation layer, except maybe at the last one to allow for negative values. So basically, a basic neural network will kind of look like this, right? So f, a big theta of x for the whole parameters will be just some affine map, and then you take the positive part, and then you reapply an affine map, etc. So why is this done? It's because it's very easy to compute this gradient. Basically, like with backpropagation, backpropagation is just the transpose of the chain rule, right? But in the case of where the parameters to which, with respect to which you compute the gradient are linear in each layer, then it's as fast to compute the gradient as it is to evaluate the map. It's just like a transpose of the corresponding linear matrix. That's why it's so fast. That way we can compute the gradient very fast, and so we can compute the gradient of some cost function that we want to optimize very fast as well. Some examples of linear layers include, well, the first first ones that appeared, I think they are called fully connected layers. So basically it's just the entries, all the entries of the matrix, of the W matrices are parameters, right? And you just find a huge linear, like you have a lot of weights, you have a lot of parameters. And every entry of each matrix is a parameter, and we call them weights. And then you apply like some sort of activation layer, and then you do it again, okay? So just like, and this is very general, because you can see that if you take, you can always find some arbitrarily small, like you can reproduce a finite element method with arbitrarily small width of the discretization, which means that you can approximate on compact subsets any continuous function for you, as long as you have a wide enough network. Now, the thing is that was a lot of parameters. Like if you have an image with millions of pixels, then you take a linear map from millions of pixels to millions of pixels. For example, that's like billions of trillions of parameters just for one layer. It's not really efficient. So instead, people came up with what's called a convolution layer, where basically, so you have, if you have an image, right, and you have, so you have pixels and you have values on each pixels, and then you transform it into another image where the value, after you put the, after you go through the layer, right, only depends on the linear combinations of the points that are neighbors to your original pixels. Right, so here, this pixel with a 0 in blue is just a linear combination of the values of the blue square. And the one, same for the one with purple, same for the one with green. And basically, so sometimes it's looked at like some kind of local average, but you can do a lot of more things, because, right, you can, if you take these coefficients as linear combinations for what happens here, well, basically you get partial derivatives in the vertical direction, for example. So you can kind of see convolution layers. Like if you instead imagine the image as a continuous function, instead of just a pixel by pixel function, you can kind of see these convolution layers as actual convolutions by something that looks like this. So an operator whose coefficients are what needs to be optimized. So a linear partial differential operator with weights as coefficients multiplied by some kind of smooth cutoff function. And that's kind of why it's called a convolution layer. It looks like you can kind of justify it looking like that. Okay, so that works for images, but when we want to study more, well, surfaces. And so for surfaces, you don't have like this nice pixel structure. So there are various ways to do graph convolution, it's called. It can be done using the graph Laplacian, but in the case where the graph comes from like a mesh structure, one of the state-of-the-art method is what is called a spiral net. Spiral net plus plus, there's a lot of variants. But the idea is, so it only works when you have a fixed graph structure on all of your data, right? You work on a data which is composed of meshes which have the same mesh structure between different meshes. And so what you do is, for each point, you look at a spiral of fixed k point. Fixed, k is a hyperparameter to fix at the beginning. And so you take the first, so you can either take it at random or you can take it, you can take the closest point or something. So you look at the one of its neighbors, and then you run along a spiral by following the triangular mesh structure. Right? So this is the central point of the spiral, and then you take some neighbor, which is the next point, and then you just follow in the like you either chose like direct or indirect rotation, but anyway, you follow the next the triangle to which they belong to, and then you follow the next triangle and the next triangle, the next triangle, and so basically this gives you, like, for each point, a fixed spiral which corresponds, like the indices of each of these points in the graph. Since all the mesh in the data has the same mesh structure, you will get the same spiral in every mesh. And so then if you have some kind of value attached to each point of the mesh, for example, like the place where the mesh is in the ambient space, then you can take linear combinations of all this data and that belong to the spiral and get a new feature, a new value for your feature at the start of the spiral, right? And so for every point, you have a pre-computed spiral, and then the coefficient of the linear transformation will give you are the weights that you optimize, and it's just one way to do some convolution in the same way as you had convolution filters before. Okay, any questions? Because okay, so because of this data imposition, right, spirals, they can only be computed once during pre-processing. Basically, that's the main point. And so as a result, this works very well on when you have a fixed mesh topology. But when you don't have fixed mesh topology, it can't work. Okay, so I'm going to talk now about the kind of problems we wanted to do, to solve, and then I'll show you the methods that we had to solve them. So first of all, the first thing that Thomas worked on was a autoencoder for human faces. So an autoencoder, I see it as a nonlinear version of the PCA, the principal component analysis. Basically, you assume that you have a data set. Your data set lives in some space, X. And then you have an encoder that takes you from this data to a vector space with fixed dimension, which is the latent space. And afterwards, you also have a decoder that takes you from the latent space back to the initial data space. So if you do the linear version, so it's PCA, it's just like the encoder is just the coefficient of the PCA of the, like if you have a data, you just project it onto the space generated by the first k values of your PCA. And that gives you, the coefficient of this gives you the latent variable. And then if you have coefficients for the directions in the PCA, you can turn them back into a data by just taking the linear combinations of the eigenvectors, of the PCA vectors. Okay. And now what we want is for the encoder to be as close as possible as an inverse for the decoder. That's like a lot of the first image generations were made using this kind of structure. Okay. So now what we want is to do the same, but for triangular meshes of faces and expressions. The problems compared to studying images is that, well, data can be first much harder to come by. So one of the data sets that we trained on is from the COMA data set. And basically, so there are like 12,000 meshes inside in the data set, but the 12,000 meshes are made from just 12 people who did 12 different expressions each. And so that's just 144. And what we have is also intermediate step to go from neutral expression to that expression. So even though like 10,000 or 12,000 is pretty big, or maybe it's 20,000, I don't remember how many, but it's in the tens of thousands. Actually, like in terms of identities and in terms of expressions, we don't have that much data. So, and one of the great things about that database, though, is that we have the same mesh structure and we have some point-to-point correspondence, right? So if you have a point that's on the nose on one of the mesh, it's on the point with the same index is on the nose of every other mesh, right? So that's really nice to have. But that took a lot of pre-processing works on the part of people who did the data set. And you can't really expect to get a lot more data that has the same topology. At least that's the kind of the hypothesis for the work. And so it would be nice if we could instead just add to the data set just random scans. Right? Yes?
I have a question. Why they in this data set you have such extreme expressions? It's I think it's on purpose, but why?
Okay.
It's very hard to see anyone. I don't know.
Yeah. I guess they just asked people to do these expressions during a scan, and they were like, okay, go from neutral to as wide as possible. Right? Or?
So again, answer for this is they wanted to show that we can do kind of better with neural network than PCA, and so you need kind of extreme expressions because it's the case where PCA starts to
okay.
Well, less.
Okay. So thank you, Emery. I just want to say, Emery was also mentioned.
Channels of the data.
Yeah, Emery was also mentioned as one of the authors of all of this work, right? And Emery helped also. Thomas worked on a lot of of things. So, okay. As a result, yeah. So we're missing a lot of data, and if we wanted to add new data, it would be nice not to have to do this pre-processing process of just uniformizing the mesh structure and things like that, which is just like it has to be done basically by hand, or it's very hard. So instead, we wanted to see if we could make an autoencoder that takes that can encode any mesh, and also that can be trained on any starting mesh, right? So, and the idea was, okay, first, I need my encoder part, right, which takes my face into some Rn vector space. I need it to be such that it is robust to remeshing. not only can it take into account, like not only can it take as input any mesh structure, but also it should be robust to remeshing, meaning if you have two meshes that represent the same continuous surface underneath, then the value of the latent code should be as close as possible. And then the additional specification was that it should be trainable on any set of topology, right? Because this is actually like, so even if you have this part, then you have to have some sort of loss function which allows for comparison between different mesh topologies. And I think in this group, like, it's not too hard to figure out. Like, we used like a sum of various varifold norms, right? But I don't know if everyone knows about the varifold norms, but I do have slides explaining it, but depends on. So anyway, as I said, yeah, so the general method, you take an encoder that takes any mesh or even a cloud of points into a latent code. And for the decoder, we chose to basically make use of what was already available for if you have a fixed mesh topology, because ultimately when decoding, like, you don't, since you're going to be able to compare any couple of meshes, you can actually fix the mesh structure on the output. So you can use something that like spiral net to just decode from the latent code into a mesh. And so what we did is that we increased regularity by, we fix a template. This is just a completely fixed template, like kind of hyperparameter. And then we optimized on finding a deformation from this fixed template onto, so just a vector field, right, which we follow for deformation. And we get a deformed mesh, and then we also need a way to compare, like we need a cost function, an error between the entrance and the input and the output. And as I said, this one was made with varifolds. Okay, so yeah, this is what I just said, right? We use PairNet. Now, some completely, like not completely other problem, but something that can't use as output the same, like a fixed topology, is if you want to, for example, animate a scan. So this is a scan move, which was made so that you have a source mesh which has any topology. It can be a scan or it can be anything. And then you have some target motion from some other scans, maybe some other identity, some other person that undergoes motion. So you have a sequence of scans or a sequence of new meshes, and you want to transfer this motion onto the original mesh. Another work that uses the same basic idea is, so basically you have an initial mesh and you want to deform it according to some additional information that is given to you. Here, the additional information was just some other motion of some other mesh. In this paper, Scan Talk, so we always have to have some fancy names, you know, for the networks. That's marketing, apparently. Instead, so you start with some 3D face and you add an audio snippet. So an audio of someone talking or singing or something. And then you want to animate the face in such a way that it follows the audio. Okay. And finally, so this one is, I think it's fun. I don't know if it's like the use case. I think it's fun. It's just here as input, you have some first shape, right? And as output, you have, so the same, the shape that comes from the same kind of person, like the same identity. Doesn't need to be the same mesh structure, but it should be the same identity, but with a different pose, right? And you want to have an interpolation that goes from the input to the target, but you want to be able to restrict this motion only to some part of the shape which were chosen. Right. So this has to be chosen by hand. But for example, here, you match open hand into hooked hand, kind of not closed, but kind of closed, half closed. But you only want to move the two, like the thumb and the index. And so you just put a mask, you just select this area, and it automatically deforms only the two other fingers. Yeah.
And what is the motivation for this mask selection thing?
Honestly, it's just that it's fun. Yeah. It's kind of to see if it works. You can do some nice thing. You can kind of mix and match. So, for example, here this pose doesn't appear anywhere in the dataset. So it can create different poses. It can create different things. But the motivation was kind of to
say that we should be able, you need to be able to localize.
Yes, exactly. Exactly. Yeah. Well, and the thing is, it kind of falls from the way it's been implemented. Like, it's not, I think structural constraint is maybe a little too, but okay. So basically, for these last three applications, they all use the same idea. So you have the source that you want to deform. And what you're going to have to do is to compute like a field of features, meaning a per vertex field. But I like to see it as a field of features because that way you can make the link with the continuous case. Okay, with the case of a continuous surface. And that basically gives you information, okay, this is where I am on the surface, this is the kind of things that I can do. And on the other hand, for the additional information, whether it be another shape or an audio file or something, you have some kind of global encoding. And then what you do is that at each point, in addition to having your per vertex feature, you concatenate this feature, this global code, right? So you find yourself with a feature field whose like first half of the coordinates depends on the point, but then the last half of the features is constant all over the surface. And then you mix everything up and you output a displacement field. And this displacement field, you use it to you add it to the initial surface and that gives you a deformation. So,
slowly?
Can
you repeat slowly?
Okay. Maybe I just make use of the board.
It's true. I think those are
okay.
collection.
Okay.
I think they will be better.
So you have a surface, right? And then, so this surface, you do some processing. And at each point of your surface, you're going to have a feature. I'm going to call it f of x. Or maybe it's better to use the same notations. U of x. Right? And so basically U is a map from S into some arc. Then you also have some additional information, so some global code. Additional info Z, which comes from some sort of encoding, which also belongs, I think we usually choose it the same size, but it doesn't really need to be the same size, but it belongs to Arc. Then you get a final feature map, which goes from S into R power K times R power K, which to X associates U of X and Z. This additional information. So Z doesn't depend on the point on the surface, but it's added everywhere. And then from there, we do some other processing of like a surface-wide processing, and we obtain at each point X a deformation vector. I'm going to call it d of X. And then your final surface, maybe I'll write it here because I don't know if I go down everyone can see it. But final surface, the final output of the network is the image of X gives X plus d of X, where X belongs to the surface. Is that a bit clear or not?
Yeah, okay, I understood that, but the thing is that what we could say that you had this global feature at the end, and we could say
no, but
it's really redundant, and so I think there is still mystery.
Yeah. But the thing is, the process here, like it's like the neural fields. Like it's used to combine the locality that you get in the per vertex features and the additional information. So like your network will have different response depending on the value of the features here to your global code. Okay. So to do this on any sort of input surface, you need a network, like you need transformations that are invariant to like reparametrization or to a change of mesh, meaning that they would give basically the same values at the same place on the surface if we changed the mesh that represents the surface. So basically, the main way to what we're missing ultimately is there's the global encoder for the head auto encoder, right? We also have, and then we're also missing like a per vertex encoder and decoder, and a loss function. I already spoiled the loss function for when we study, for example, the head. It's going to be variforms. But the general idea for the actual networks themselves is that they should basically consider the input as a discretization of continuous objects in such a way that the output, like that the network is continuous with respect to the convergence of a mesh towards the surface. Meaning, theoretically, basically, the mesh should be able to take as input a full continuous surface instead of a discretized version. It's just that it's impossible for a computer. But and there are a few tools that have been developed. The first is the case of networks that are continuous with respect to the Hausdorff topology. So they take as input clouds of points and they of any size, and they output something that is continuous with respect to the Hausdorff topology. And you can also have networks which are continuous with respect to measure topology, like if you understand surface as measures and then you integrate things on them, or you can do surface PDEs or PDOs with finite element methods or with other solver or things like that. And that's the general way that we've been doing this. So I'm not sure how much time I have, depending on how much detail I want to get in. But so I start with PointNet, which is the basic and kind of most general way to do a Hausdorff continuous network. So just does everyone know about the Hausdorff distance between two compact sets? Yeah? Okay.
And you probably want to recall the definition. We'll spend 10 minutes.
Okay. So basically, So we want an encoder that's defined on every mesh or every cloud of points, such that if two data represent the same object, then they end up on the same code. So for this, we're going to take an encoder that's continuous with respect to the Hausdorff distance. And just to recall, so it's the fastest way I've been able to define it, I think. You look at the space of all compact subsets of R3, and you can identify a compact with the distance to this compact. So you get a function from R3 into R3. And then what you can see is that if you have two compact subsets, the difference between the two corresponding distance functions is bounded. And then you can just take the infinite norm between them. But basically in practice, it's just like a distance between clouds of points. So yeah, no, but it's I removed it, the actual definition, because I wanted to go faster, but maybe it's not, as a result, it's less intuitive. So. Okay, but basically what you can see is that, yeah, if you take a cloud of points that really represents, that is almost dense inside the compact, then the distance between the cloud of points and the compact is zero. Is almost zero, and so it's a distance that's appropriate for what we want to do. And yeah, that's what I was saying. If you have two cloud of points that represent the same object, as a result, the distance between them will also be very small. And so if you have an encoder that is continuous with respect to this, or even Lipschitz with respect to this distance, you will get something that satisfies our conditions. The problem is, okay, what kind of functions are continuous with respect to the Hausdorff topology? That looks, it looks a bit abstract, right? But actually, we have a basic example. So you just take a regular, like just a continuous real valued function on R3. And then to any compact set, you associate the supremum of this function on the compact. And you can check that actually this is a continuous map, right? With respect to the Hausdorff topology. Like if K1 and K2 are very close, then the supremum of the continuous map on K1 is also close to the supremum of that map on K2. And the main result of the article for PointNet is that basically every continuous function on with respect to the Hausdorff topology is a combination of such functions. In the following sense, basically, so you take any real valued function on the space of compact subsets of the ball, right? And any distance epsilon. And what you can see is that for K big enough, you can find K maps from R3 into R, such that, and a map from Rk into R, such that if you consider the map, which is just the combination through G of the maximums of the HIs, you are epsilon close to your target function.
So what are the assumptions on H?
Continuous.
Maybe. Where is it written on the slide?
Yeah, it's not written on the slide, but yeah, it needs to be continuous. Otherwise, the functions themselves wouldn't be continuous with respect to Hausdorff topology, you know. But the proof is in the paper of PointNet, I think.
And is it okay? So how do you prove it?
I think the proof of the intersection.
Oh, really?
Okay, so do you know how to prove it?
No, I don't.
So I think like you can kind of use the same, like I would kind of, I think you can kind of use the same process as when you prove that.
Invariance class and plus essentialist invariance.
No, I don't know, like, it feels like you could easily, like, you know, for example, you separate your ball into like smaller and smaller voxels, right?
But okay, so it's really mathematics here. There's no voxel.
No. I'm saying, so, you know, the proof of the compacity of the Hausdorff distance, I mean, of the fact that the set of compacts within a compact subset is compact. It's done basically through this, like you use voxels and you just use points that are inside the voxel, and you know you say, okay, the compact does have an intersection with this voxel and things like that. But and
okay,
but it's been a while since I looked. I didn't realize it was wrong. So, you know, maybe yes.
If you go to the archive version of the paper and you download the TIC file, then you can read the comments in the TIC file. And there's some points in there that help you complete it. I remember this because I gave this paper to like a student at a seminar. The student came back to me, asked me to explain the proof, and I realized what the hell's going on here. That's the only thing I remember. Because I was a student for a while, but I think that's
okay.
So the proof is lacking something, or
yeah. And the original version of the proof is lacking in some steps and some assumptions also, I think. But basically, it's like this: somebody construct a grid, and then you basically for that get there, so you can get this grid positions falling out, and then you can solve choosing your functions.
Okay.
But I guess it's very bad in terms of the approximation rate.
Yeah. And you do have, like, you take one function and then, like, you don't know how many k's you need to have. You know, it's okay. And then you use, then you say, okay, but any continuous function can be approximated, at least on compact subset, by a fully connected network. And so what you do is just, you take fully connected networks for H1, etc., HK, fully connected network for G. I mean, a multi-layer perceptron, actually. So a combination of fully connected and LU. And that gives you that gives you the potential to approximate a lot of continuous maps within the Hausdorff topology. Okay, so yeah, that's I don't really have to do this. So anyway, yes, so that's what I was saying. Basically, as an encoder, you just take H1, Hn are both networks that go from R3 into R, right? Just multi-layer perceptrons. And then you take the max value over all the cloud of points of each of these maps. And then you combine all of them through another fully connected network, which is called G. And so you can, and so it's pretty fast, and you do get an encoder that is continuous with that you can apply on any size of cloud of points or mesh, and whose output is continuous with respect to the Hausdorff topology. And so that's what we did for the autoencoder of human faces, where as an input we just use this point net, and so as an output we use spiral net. Okay, so the nice part about this is actually, so if you don't mind just training on the initial set, if you just want something that can be applied to any scan, but it won't work as well probably as a fully trained one, you can just train it if you own a data set on which you do have full correspondence. And then, because your encoder is still automatically robust to remeshing, you still obtain results. So this is the kind of result you can obtain, right? So this is we input various targets with various remeshing inside our encoder, and then we decoded it again, and we get basically the exact same face. We also use this as an encoder for the motion transfer, meaning for the motion transfer we just in order to, because it's still a pretty rough encoder, but it's good at telling you, okay, something is here, something is here, something is here, right? And so for a motion transfer where we had a sequence of motions that we wanted to transfer on a template mesh, to encode the motion and get the global part of the encoding, basically we just put each of the shapes during the motion through a point net encoder, and that gave us a sequence of latent codes that we could then apply and put onto our surface.
So what is a sequence processing network?
Yeah, this one, it's called a gated recurrent unit. I think it's one of the basic kind of thing that's used for processing some kind of time sequence. I'm not big.
Yes, how does that work?
I'm not sure. I think it's pretty similar to some kind of transformer, but I'm gonna be honest, I don't really know the GRU. But there's a Wikipedia page, but it's not like a transcendental new thing. Like you just take various scalar products between things of the sequence and you use those to kind of.
The time information it's where after in the latent space.
Okay, so each.
If you think about your
picture,
say,
no, I haven't described yet how to then exactly do it, because you do have you output for each instant of the motion, like for each frame of the motion, you do get as one latent code. And so then you can, during the decoding, like you're gonna have at least like the Z will depend on the time.
Yeah. No, but because you in this you say that you are adding this Z.
Yeah.
On the field.
Yeah.
But in fact, you have no field. You have.
Oh no, that's because this is the global encoding, right? So you would get ZT, right? But there's no field on this one. The field is on the surface on which you want to transfer the motion.
Okay, no, but because the point cloud, the point net is eating.
Yeah, no, there's no field.
Point cloud, so it's not something you. So there is no.
No, there's no local information. There's no local information. I mean, maybe if you look deep inside the latent space, you can find some sort of local information, but there's no obvious local information on this.
Okay, but I have a much more basic question.
Okay. Okay.
To be super clear, Sylvain. In your previous network, so you display things as meshes, but as far as the encoder is concerned, it's just a point cloud.
Yes.
And then you just use the topology of the template for your spiral.
Yes. Yes. Exactly. Yeah. So you could, like, we tried, but it doesn't seem to add much. Like you could instead do this, instead of on R3, you could do it on R3 times S2. And add like the normal information on the centers, things like that. It hasn't seemed to improve that much the network. So I mean, you get small improvements, but visually you don't see the difference.
Okay, and also since in the point net architecture, so you don't really have sums, you use maxima.
Yeah.
Fundamentally, because you do not understand your shapes as measures but as sets.
Mm-hmm.
So does it mean that, for instance, if you add speckled noise here and there, it's going to be very sensitive to that?
I think, what kind of noise?
I mean, if you have some outliers.
Yeah. Okay. Yeah, I do think it can be sensitive to like far outliers. Yeah.
So because in a sense, if you
Yeah,
have
absolutely.
your human silhouette with arms like it, but 2 points here and there.
Yeah, it can be.
To believe that it's
Yeah, absolutely. Yeah. So. Okay. Now, yes. So I don't think I want to go too much into the loss functions. Like I already told you.
Because you have videos. Are
Yeah.
you going to show them?
Yes, supposedly.
I was wondering if you had forgotten.
No, I haven't forgotten. No, because like this is not like there's no videos here. I mean. Okay. Anyway, so the loss function. I think I'm gonna pass it. Like everyone knows about varifolds and how to use them to compare surfaces, or no? No, not at all. Okay. Yeah, I still think I'm gonna pass it because it's so late. You guys probably can't. If you want to, I'll come back to it. I don't even know if it's the best presentation to understand it.
Yeah, but in a nutshell, because what you presented so far, it's three shapes as sets.
Yes.
And now you want to understand shapes more as weighted sets.
Yeah, but ultimately, so basically, for the loss functions, what's been happening is that it worked for faces, but it didn't really work for the rest. Like for example, for the faces, it was less. It was worse than just using a chamfer distance, which is not great either. But
what was worse, using Hausdorff against Champ?
No. I'm talking about as a loss function. So using varifolds as a loss function against the chamfer distance. Okay. But yeah. Basically, the varifold and currents and things like that, they just say, okay, so one way to be independent of a remeshing is to understand surfaces as measures, right? And then you integrate things onto those measures. And then if so you can discretize you can discretize a triangular mesh by just it being a sum of Dirac masses that are with weights that are equal to the areas of the various triangles. And then you use a kernel function that you put as a hyperparameter to easily compute distances between measures. And that's what you use as a loss function. And that way you get something that's completely, that's very robust to remeshing. You can either, you can show it very, it's not that, you can show it mathematically and you can test it numerically. That usually it works. Okay. Okay, so here I did some, these are some results of the autoencoder for heads using a sum of varifold norms for the loss function, but trained on so this is trained on the comma set, so on the actual data set, and this is when it's trained on the scans that correspond to the comma set. Actually, you can see that you do get something, but I don't think it's that great yet. On the other hand, you don't have more data. You just have rougher data that comes from the scan. But it's for now it's still better to train, even with the varifold distance. It's still better to train with the varifold distance on the original data set, which doesn't really.
Okay. So to be clear, the third row is a row scan.
Yes.
The fourth row is what you get when you train on the row scans.
Yes.
And then in the first row, it's like pre-registered meshes.
Exactly.
On the row scans.
Yeah. And then, just you get something that you can do with a lot of autoencoders. So you can do an interpolation, right? So if you take two So it's on the left and on the right, two initial faces, and you compute their latent code. Then you just do a linear interpolation of the latent code, and you decode this linear interpolation, and you get things that are relatively satisfying, I think. You can do extrapolation, which is the same thing. It's such you go further. You have your two latent codes here, and then you explore what happens when you go further along the same line in the latent code, and then you decode what you get. So this works way less when you look at it than the interpolation, which is kind of expected. And you can do some sort of arithmetic on the latent space, right? So if you had a face and you know its expression, but you remove, like you encode it, and then you encode another face with the same expression, and you do the difference between the two codes, but then you add like some other expression, such as the neutral expression, you get something that looks like a neutral expression on the original face.
And the question is, because you encode your thousands of meshes in your space of dimension 128, and in your experience, do the codes cluster on some kind of structure? Or
Well,
is it fully unstructured, like your isotropic Gaussian?
I actually haven't. I haven't actually looked. My like clearly, like if you look at the interpolation, for example, clearly, basically, so these are all. So actually, these specific ones aren't in the latent set, but like because otherwise it would be a pretty useless experiment. But you have other identities with the same expressions, or other identities but with different expression, and you know, in the latent space, you have a lot of all the intermediate steps. So this seems to indicate that it has a tendency to send things that are like that have a lot of like things that look like path in the initial data set. They get turned into linear path in the latent space. This was not optimized for, you know, it's just, it turns out like this. I don't think it's that surprising when you compare to other latent spaces. I think that's pretty, but if you look at the structure of the data, it's kind of like this, right? It's like you have 12 identities, and for each of these identities, you have like 12 paths inside it, right? And so the paths are kind of parallel to one another, because like if you just do a linear transfer of phase deformation, it doesn't work that bad, you know. That's why the PCA originally kind of worked in the comma subset. So like it's not that odd that this pattern that's repeated between all the identities and between that it would be encoded as just a segment in the latent space, I think.
Can you? No. Go ahead. Can you explain this arithmetic?
Oh, basically, so the idea is, so each of these you input in the encoder, so you get latent code, right? And the
No, I know the story about queen minus n plus woman equals.
Yes.
King minus men plus woman equals queen. But this in this situation, it's not that clear, because when you make the difference between two, it's the same guy, no?
No, it's not the same guy. So this is like
there is two different guys. So what?
So these are the same guy.
Oh, okay.
Yes,
okay.
These are the same guy.
Okay.
Yes. Okay, is that clear?
Yeah. Okay. I was thinking.
Yeah, and of course, like this arithmetic in the latent space doesn't depend on meshes, on the mesh structure or on the solution. So there's a lot.
Do you really check that? This arithmetic, because I'm curious about knowing it.
How, like, beyond doing a couple tests? No.
That you can produce something which looks like this. But
Yes. We didn't do all of the couples of, we didn't do it.
what's going on?
Those were chosen at random, but like we didn't look for one specifically where it worked, but we didn't also look for all of them and to see if there was something that doesn't work. Yeah, that's true.
No, that's
Actually, in a way, I'm not sure if this is quite convincing on the chip. Okay. So there are a lot of limits. One of the limits is just sometimes a change of expression. It kind of it's very similar to a change of like a parametrization, right? Like,
So, I'm sorry, I'm upset by this. Why it's neutral, the right? No, just the example before the subtraction. I'm sorry that. But can you explain what that is? No, the very.
okay. So the idea is, so you remove, you have like identity and the pose.
Same identities on the two lefts.
On the two on the right. So you have one identity and pose. You remove same pose, but different identity.
Oh, it's supposed to be the same pose?
Yeah, yeah.
Oh. Because it looks okay. Okay.
And also, what would you expect?
It's not okay. It's really.
If instead of being A minus B plus C, you just see A minus B. You usually go out.
Yeah, probably. That's my expectation. But I don't know if the result would be just something that doesn't mean anything, like complete chaos, or if. Okay. Okay.
The fact is that sorry, but that fact does not look as the same pose for
You think so?
Yeah. Okay. They're open now.
Okay, it was selected as the same pose in the comma, but I see what you mean. Yeah, it's true that it looks more like this pose. Okay. Yeah. Yeah, I'll have to ask Thomas.
Thank you.
Okay, so last part of the talk. I didn't go into as much detail. I just described roughly what happened. So hopefully. But you'll see. Anyway, what we're missing is this, right? A way to get per vertex features and a way to decode per vertex features plus like a constant feature field into a displacement. So the first thing to do is to create some kind of per vertex feature, and we still want it to be created in such a way that like it's consistent with a change of mesh. Actually, that's not too hard. Like the first thing to do is just as the initial feature field, you just take the coordinate of the vertices, right? And so you see, if you change a mesh, well, the coordinates change a little, but like as representations of a continuous function, they represent the same function, right? They represent the same surface. So, and actually, usually, if you can do this, depending on what you want to do, like that works very well. You do have some problem. Like as a result, you depend on your orientation. For example, like you're not invariant to just a simple rotation. Like if you rotate your mesh, everything goes to hell. But if you don't want that, you can get like for example, what they called heat kernel or wave kernel signatures, which is just so. Basically, you solve like like PT is just the heat kernel with respect to the Laplace-Beltrami equation, and you just look at its diagonal at various. That's one way to get signals which are like purely intrinsic. And they don't depend on the remeshing as long as the remeshing is like it doesn't change, like you don't have holes that appear or things like that. But we haven't been using this because it doesn't have as much precise information compared to just the place where the vertices are. Okay, and now we need to, oh, right. Yeah, I don't think I mentioned that. Okay. One of the networks that has been developed and that seems to work pretty well to transform like a per vertex feature into a new per vertex feature and to process it is something that's called diffusion net. And basically, if you recall, like convolution networks, which work so well on images, they can kind of be seen as a convolution with a partial differential operator and a cutoff function. And well, the Gaussian is almost a cutoff function, and the Gaussian is the heat kernel. So, well, how about we just solve the heat equation on the surface heat equation. And that's the basic diffusion network. So basically, you start with scalars per vertex features, right? And you diffuse them through a heat equation for a time which is one of the parameters of the network. And that tells you how far from your starting point you're going to look. You're going to look around your starting point for other information. You're going to do a kind of local mean. And how far you go for your local mean is with the time during which you diffuse the equation. Then you do some other stuff. So here, the way they do it is like they take the gradients of the various scalar features that have been diffused, and then they combine them with like per vertex MLPs, and they add it to the original. Anyway, you get a new vector, feature field. So this part, like, it's not too hard. The part of combining the gradients, taking the gradients and things like that. It's just it could already be done, you know. But the problem is how to solve the heat equation in a way that's pretty fast, right? And the way that they usually do it, depending on the size of the mesh, is that you have your Laplace-Beltrami operator, or its discretization, and you just look for the first 128, usually it's a power of 2, but the first 128 frequencies, and you project onto those frequencies, and then the heat equation becomes very easy to solve. So one of the problems is that to keep computations reasonable, we do have to cut off high frequencies, but it has seemed to work well. And weirdly, it's been relatively robust to things that I thought would completely make it collapse, which is adding holes onto the mesh. Right. So here, this is like a heat map of the norm of the features that have been processed with the heat equation, and you see that they don't stay exactly the same. They do stay relatively the same. And I would have thought like solving this equation, especially after cutting off the high frequencies or something like that, I thought it would cause some trouble, but
because it's general. Because it's more holes. With big holes, it would make a.
Yeah, maybe. Yeah. That may. Yeah. Yeah.
Yeah, because it's like very, very high frequency, and for it doesn't impact, like the cutting is like so low for both that it works well for both. But like if you have a hole that's gonna like when you can see the influence is a eigenfunction, two eigenfunctions, there you're gonna see a big difference. Like if you cut the shape, that's gonna be
but that's why but you know, like I think like the first eigenfrequencies has to do with the longest geodesic, and sometimes like if you, I think, but sometimes like if you put small holes, like even the first frequency can just deteriorate. So that's why I thought small holes would be hard, would have a chance to collapse, but. Maybe I'm just not familiar enough with.
I think the biggest issue is cutting in half is a big issue.
Yeah.
No. But it's strange because even if you diffuse at a place that's exactly the same, but like kept intact, because like the cutoff frequency is very low. This has a huge impact. So it diffuses like less far for some reason when you have the full mesh, whereas when you have half the mesh, it diffuses like much further away.
Okay.
Or the opposite. No, the opposite.
Yeah, already, yeah.
It's what are you displaying?
Yeah, it's the norm of the processed features after they've been through like a few layers of diffusion method.
So you have those three basically identical shapes. You had one input feature somewhere.
Yeah.
You process it, and you just remark that
Exactly
the feature maps.
Yeah,
the
yeah.
3 layers. They look
Yeah,
consistent.
yeah. Okay. Now, for yeah, maybe I just go straight to the videos. Okay. Yeah, this is the ultimately it's not. I just think it needs to. Sorry. I don't think I have time to explain all of the network ultimately, and I don't think I can talk about it afterwards. But like this is the scan move to transfer a motion. So to transfer motion on an initial scan and scan talk. So on scan talk, I do have videos. Okay. I don't know if you will hear though. We'll see. Oops. So for example, so this is the cleanest one because it's like, oops, sorry. Okay, and you can do other things that are very far from what was in the training set, but it looks much worse. Oh, sorry.
Yes, I know who lives on Drury Lane.
So the thing is, the synchronicity of the lip motion is good, and like it's better than or as good as state of the art with fixed topology. But if you ask like someone who can read lips, he will tell you, "Oh, this is absolutely this has nothing to do with." So usually the evaluation for this kind of problems is focused on the synchronicity with the lip, but it's like a lot of things with these kinds of networks. Like it's okay, but it's so far from perfect, and it's not clear how to get it perfect.
What is exactly the training set?
The training set you have like 3 different talking heads training sets that all have that have all been made to talk on the same kind of audio snippet, like a few audio snippets. These were all audios that were not in the training set, but you have various phrases that are used, and the person talks, and they've been scanned, and then you do have on the 3 different databases, you do have point-to-point correspondence.
Okay. So if you want to animate someone, you take picture of someone here, scan, and if you want to, what would be the process?
So
you use this thing.
Yeah.
What would be the process?
Well, you would need to get them inside like a scanner that gives you something about as precise, and you just input some audio snippet and the person and the scan, and that should work. But notice that the voice is not consistent. Like it's just the same audio file, right? You don't adapt the voice to the person talking, and all you get.
So, you have that step to go from the scanner to the.
Yeah, so the audio snippet is encoded with a known network for encoding audio, which is called Huber. And then you have like LSTM, which is another way to add some consistency between, like it's another way of processing like sequences of codes, of latent code, to get another sequence of latent code, basically. Okay. So I think this one is kind of interesting. So this is another way of, like, this is to decode. Actually, so just in the case of motion transfer, like the decoder was just what ended up being fast enough and working is just a shared MLP. So like once you have all of your sequences of latent codes and things like that, at each point of the surface, you do the same MLP, and that gives you a deformation vector, and you apply the deformation to like the previous step of the sequence of meshes that you obtain. It's but when it comes to scan talk, what worked best was just like the decoder is also a diffusion net, right? And you just process features until you get, and at the last layer you get a three-dimensional feature which you interpret as a deformation vector, and you move in that direction, and you get your deformation and your which allow you to make someone talk. But another way to decode deformation is what is called neural Jacobian fields, which, I mean, I think it's pretty fun. Basically, once you have all of your features that are processed, you just, the last process will give you features on each face instead of each vertex. And it will be of size 3 by 3. And so you get on each face a 3 by 3 matrix. And basically then you restrict it to the tangent space, to the triangle. And you say, okay, actually this, so you get a linear transformation from the tangent space onto R3. And you say, okay, actually, I want this transformation to be the Jacobian of an actual deformation, right? The differential of an actual deformation. So it won't be like, obviously, you won't have, because of the way it's done, like it's the same as computing 3 different gradients, you know, surface gradients, but you know, not every vector and not every tangent vector is a gradient. So you have to do like a Hodge decomposition, and you have to solve the part of your linear application that is actually the differential of an actual map. And you do this by just solving the Poisson equation with respect to, again, the Laplace-Beltrami, and you get your deformation. And the nice thing about this is that it kind of smoothens your decoding signal, which is what allows us, in the case of the partial interpolation, to just put some very rough mask instead of computing or things like that. So, like, you know, if you want, so you want to just close the 2 fingers here, what you do is you compute all of the per vertex features, right? Compute all of that. And then right before you solve the Poisson equation, you put those that are not on the fingers you chose, you put them all to 0. The other ones, you keep them the same. You solve the equation, the Poisson equation to get your deformation. And that way, it's much smoother. So here, maybe I just first show some video. So for example, here, all we had was this and this, right? And then we alternatively during the videos put a mask on some fingers and not on some others, and did a linear interpolation of the latent codes to get the interpolation part. So get.
So what are we seeing? I didn't understand, sorry.
Okay. So for here, what happened is, okay, this is turned into a latent code, okay? And is spread all throughout this surface. Then we do the processing, and we cut off everything until here. So everything here is 0. Then we do a linear interpolation from from 0, so the neutral pose, no deformation, onto the latent code that we obtain here. And so that's what gives us the first motion. And then afterwards, once we stop, then we keep this code the same, and we add back a new linear interpolation of the same thing on the third finger, etc. And then we do it in reverse with going back to 0. We also have this one where here we do like a partial interpolation from neutral pose onto a combination of 2 and 3, because then you can kind of mix and match poses, right? Because you can put a mask on the first pose to only have some part of it be followed, and then put another mask on the other pose, and then combine them. And let's okay. And this is the non-video version.
So everything is really related to this question.
Yeah. It's not everything is, but the fact that it's smooth and not just like here you have a long deformation vector and then suddenly it goes to 0, and so you have like discontinuities and things like that. It comes from going through solving a Poisson equation to have some higher regularity.
No, it's not.
So do you solve it online or offline? How do you do it?
What do you mean online? During the inference?
How do the video? Do you need to solve Poisson equations?
No. You solve the Poisson. Wait. Yes.
And so do you have any way to solve it fast?
Well, since okay. Actually, so what's
Real time, all that stuff.
I think so. I think solving the Poisson equation itself is relatively fast. It's the actual like projection on all eigenvalues, but
Same thing.
No, but it's
yeah, it's not a big mesh in this one here. But yeah. You do need. Although wait, but it's linear, right? And we do linear interpolation. So
in Poisson equation?
yeah. Wait. Yeah. No. Isn't it?
Yeah.
Like it's a linear Poisson equation. So yeah, it's linear. No. I'm not talking about the computation cost. I'm talking about like, we have like a latent code. So we solve the Poisson equation. Okay, I'm sorry, I'm not. Yeah, but so that's kind of that's part of what I was thinking about, but I don't know if like having an actual inverse of the Laplacian is that much faster than just solving it at each time. It would be faster.
I mean, I think like in the inverse of a differentiation is like linear, I think, maybe n cubed, and the computing is n to the power 3. And I think, if I remember correctly, in diffusion that they also do something like a spectral positioning.
But
Positioning and do the inverse.
no, but that's the thing. Like, I think.
You don't do it in your code. It's just you're solving it on the fly.
Yeah, I think so. Yeah. Okay, I just stop here. Thank you for attention. I know it was pretty rough, so thanks for staying until the end.
So what is Poisson?
Yeah. So this is like we haven't used it. It just came out in a different paper, but here it's another way of processing features like per vertex features by just basically. So you have per vertex features. You take the gradient, you obtain like per phase gradients, and then you do like some sort of processing, like an MLP phase by phase, a shared MLP on the phases. And then you solve the Poisson equation to get back to a per vertex feature. And what the paper says is that just solving the Poisson equation is much faster than computing the first 128 frequencies, at least if you only solve it like a few times, And so, and you don't cut out high frequencies when you do this. And so that would be one possible way of, like, I wanted to show everyone the tools that you can use to do surface processing that doesn't, that work, that's robust to remeshing. So that's why I was mentioning it, because the paper seems to have very good results, but we haven't tested it. We haven't tried like overhauling our whole architecture to try it.